Okay, so let's first of all finish this lecture for the microbial growth. Just remind you, very important for the growth curve, we had the lag phase, log phase, stationary phase, and death phase. That will be mentioned twice. Then we finish talk about the factors that affect the microorganism growth. So we call it the pH, and based on the pH, we could separate them into acidophile, neutrophile, and alkalophiles. And then we talk about the temperature, because the temperature will affect the enzyme function. So every microorganism has their minimal, maximal, and optimal temperature to grow. Therefore, we have a different category. And then this slide, which is have the temperature ranges for the microbial growth, including cycrophiles, cycrotrophs, mesophiles, thermophiles, and hyperthermophiles. And I said the cycrotrophs is very important for regarding the food safety, because like Listeria monocytogenes, they could grow in the refrigerated temperature. So even you vacuum package, you put in the refrigerator, it's still going to grow if there's a bacteria there. And most of the pathogen, like Salmonella, it is like E. coli, it is mesophiles. So that could be grow up to 45 degrees Celsius, even a little bit like warm temperature. They could grow, and they can grow very well. Then we're spending a huge time talking about this water activity. And that is an important concept. Now, said very simple, water activity is available of the water, could be using for the bacteria, and it is related to the vapor pressure. So that's something we are spending lots of time. And then, based on the salt for the bacterial growth, we have halophiles and extreme halophiles. And I said a very easy example for halophile is Staphylococcus aureus. And that's a bacteria normally happen on the skin surfaces, because more or less on the skin surfaces there is a salts. And the extreme halophiles, usually it's in Great Salt Lake City, the Salt Lake. And then we also talk about at the end, we talk about the anaerobic, aerobic, facultative, microallophilic. These categories really depends on whether the bacteria has SOD and the catalase. Because during the metabolic process, they're going to generate the toxication material. So superoxidized gas mutase and the catalase could be hydrolyzed those things, because the bacteria cannot tolerate oxygen. Oxygen for them is a toxication. Here is something we want to mention to you is that this is in the microbiology lab, we always do a little bit cheaper. We do is these anaerobic jaw. And this jaw itself is not cheaper. This is a roughly $400 to $500. And I said the chamber here is much more expensive. That chamber, if you're really looking for the chamber here, the chamber, it is about $20,000 north, so above that. So most likely in the lab we do those stuff. So how that works? There is a different stages. In the old time, we put those petri dish there. Okay, we put all the petri dish there. Usually it can fit about 10 to 12. The petri dish is agar like this, so we put it there. And then we have to create this anaerobic environments. So how we do? We put something here, a bag. This is called a gas generator. Or we call it a gas diaper. It's like a baby diaper. And these type of things, we need to add water there. Usually add 10 ml water. And what are the stuff they're going to generate? They usually generate is hydrogen. Because in these jaws, they have oxygen, so hydrogen working with oxygen will generate water. Therefore, this oxygen will be gone. So there's a reaction there to remove oxygen and become anaerobic. Now, how do we know there is anaerobic generated. How do we know there is no oxygen? We usually put an indicator. This indicator is methylene blue. Because the methylene blue will be faded, become colorless. If the methylene blue becomes colorless, then, which means the oxygen is gone. There's no oxygen there. Now, sometimes we also want to have this hydrogen and oxygen generate water. The reaction happens real quick. So we add some called palladium there, we add. Okay? Somehow like a catalyst to let the reaction happen more quick. So this is all the time what they do. Right now, because of the technology developed, you just put a gas generator there, gas sniper there. They will generate those so-called anaerobic gas bag. So you put a bag there, you seal it, that's all. And the same thing like a microaerophilic. That is what we do in the lab to cultivation Campylobacter. Microaerophilic is the same thing. You put a microaerophilic gas bag there, it will be automatically created. That's called a microaerophilic bag. Sometimes we just say can be bag, which means it's a Campylobacter bag. Then automatically we'll have 5% oxygen, 15% carbon dioxide, and the left is nitrogen. So there's a different develops. And these gas bags also expensive, a lot, about $5 to $10 a piece. So I just want to tell you, it is relatively difficult to grow for these anaerobic bacteria. And the microaerophilic bacteria for Campylobacter is very tough, so we call it a fastidious bacteria, which means it's very picky. So normally, I have students will tell me, I pick them grow in the tropic soil grass, it didn't show up. I streak them onto tropic soil agar, it didn't show up. Why? Because they need a very strict environment, extra nutrition to grow. At the same time, they are very toxication for oxygen. So let's say I'm doing E. coli. I have a 10 plates there. You could inoculate a bacteria on 10 plates, then go have a lunch. Come back. That's okay. They put them into the incubator, they're going to grow. You can't do that for Campylobacter. If you do that for Campylobacter, you come back, it's all died because they're exposed to the oxygen. So it is very interesting. It's very ironic, I always say. Campylobacter is a risk for poultry meat. However, it is very difficult to grow in the lab. And it's very interesting to see what we found, and lots of the research showing the chicken legs, chicken drumstick, wings, if you ground it, if you treat it, the Campylobacter doesn't grow. Egg surfaces doesn't grow. Feeds, in chicken feeds doesn't grow. Where they grow? Skin surfaces. Why? Think about the chicken skin surfaces. There are lots of the dots, lots of the niches there. At the niche there are less amount of oxygen. So it's a perfect microaerophilic environment for Campylobacter to grow. So it's very interesting. It is difficult to grow in the lab, but it's a risk for the industry. Okay, the next one I want to talk about briefly is the biofilm formation. This one you could talk about here the whole day. So that's called a biofilm. This is a matrix, a group of bacteria forming a matrix, 3D matrix, I will say. And it is very interesting where they generate. Okay, let's say this is a food cutting board. A food cutting board. Today I'm preparing ground beef, let's say. I'm cutting ground beef. Okay, I cut it and I slice it. That's a ground beef. Okay, after doing this, I'm going to do a cleaning, sanitizing. using detergents, using bleach. However, I didn't do a very good job, so I left some moisture there. Now, more or less, the surface has some moisture, and we call it water. And if you do not do a good sanitizing, what happens? The food soil will be there. What we call the food soil? The residue of protein, lipids, sugar, the residue of those. Protein, lipids, sugar. So which means more or less there is some of the nutrition. Then what happened? The bacteria in the environment or originally in the food surface, they started to grow. They start to grow. And obviously some of them will be dislodged. Okay, we call it dislodged. But some of them will still be there. Even one cell, couple of cells. And then more and more they're going to grow. They are attracting some. And they connected each other based on Van Waals force. This is not a very strong molecular connection. Remember we talked about ionic force, ionic bond, covalent bond, and the hydrogen bond. Van der Waals force is not a very strong one, so they connected it. Okay, they added it. And what happened? More and more they go, like this, little bit heavy. And in this poor nutrition surface, they have to grow, they have to survive. They are going through a very special cell-to-cell communication. And we have a terminology for that called QS, chlorine sensing. For gram-positive bacteria, gram-negative bacteria have a different chemicals, so we just skip that. It's called chlorine sensing. Acronym just say QS. It's a cell-to-cell communication, so become more and more sick, more and more sick. Like this, like a mountain. Like that. And then become a matrix, 3D matrix. Of course, some will believe, some will be stick there. So if you didn't do very good sanitizing, it looks a smear there. Now, the remaining problem. So in the second day, if the quality assurance manager go to the plant, he sees something happen, he say, okay, go ahead to clean it, re-clean it. Can you do that? Yes, you can do. However, the concentration to killing these type of biofilms, it is extremely huge. So for example, 5 parts per million hypochlorous gases could kill, let's say 5 log, 10 CFU per ml E. coli, let's say. This is what we call vegetative cell. Vegetative cells, which means a normal cell grow in the broth. So for example, the cell grow in the broth. This is vegetative cell, normal. Okay, if the smear comes out, what happened? This is called a biofilm. How many you need? You may need 500 to 1,000 ppm of hypochlorous gases to kill it. And sometimes that concentration is not even enough. So what we need to extend the exposure area and using surface tension. Okay, based on theta, which is a surface tension. Then rely on what? Need surfactants. A common one, twin candida. That's a surfactants, which let the antimicrobials extend the area to let them more exposed to the matrix and break down the matrix. And it is very difficult to do. And I want to tell you, the biofilm is a big risk for the meat industry, because meat, once they grounded, when they treated, there's a lots of the dust there. Therefore, every meat plant needs to very strict to have SSOP plan. It's called a sanitation standard operation procedure. If you do not do the good job of that, it's very hard to control the pathogen. Therefore, SSOP we always call it's a prerequisite program. Acronym is PP. Prerequisite program of HACCP. You heard about the HACCP all the time. Sometimes even products, commercial products or food products, you see the label said it's HACCP certified. That's what the HACCP for. And we'll talk about that, hazard analysis critical control points. We'll talk about this later on. That's why the sanitation is important. Because otherwise this biofilm will be there. It's hard to sanitize it. Now, because it's a 3D matrix, so which microscopy will be the better to use? It will be a laser confocal microscopy. Is that right? Because laser confocal microscopy, we can see the 3D images. Or we can do scanning electron microscope, because scanning electron microscope, we would see the 3D matrix on the surface. And we will not see in the inside, but we'll see them on the surface. Okay, so this is biofilm. Okay, so we finished this part of the talk. We're gonna move on to the next one. We'll talk about the bacterial medium, basically. This is not a very easy concept. We will talk about it in much more detail, and I have some examples we'll explain to you. Since this is no lab, so these medium sometimes it's hard, a little bit hard for you to understand it, because there's lots of chemistry behind that. So let's talk these one by one. I'm gonna move these first. First of all, bacterial growth, they need a medium. The medium basically is in the lab, which means we made something to let them grow, to let the bacteria grow. And they could be solid, could be liquid, could be semi-solid. So you have an impression. I have a broth with beef extract, with peptone, traptone. So let's say I have a broth. Okay, I have a bacterial medium. It's a neutral broth, let's say. It's a liquid. Now it's not just a liquid like it's very simple. We do. There is ingredients there. What are the ingredients? Water we needed. Of course, we need salt there. Sodium chloride we need. We need some nutrition which is called beef extract. That is why the ground beef is actually a good reservoir, the good medium for bacteria to grow. We need some of the protein, which is called derived protein, called peptide. And we also need some other protein called traptone. And these are relatively basic ingredients for nutrient broth. Okay? This is, and then we have agar. So I bring some agar, let's say nutrient agar. And I bring one here, you can see it. It's very simple. Solidified in the petri dish, looks like this. That's agar. It's a nutrient agar. No color actually, but it looks like a little bit light yellow. So it's agar. So this is simple category. What is that? This is solid media, and this is a liquid media. And this is based on what? Based on physics status. So based on their original physics status, we could be categorizing. We're going to talk about this physical status. We have liquid medium. We have solid medium. This is Bloss. Solid medium is agar. What else do we have? We have another one called the semi-solid medium. Semi-solid medium we don't use too often, only one time. We have a king cap too. Very tiny, not large. We're going to add a medium there. It's a semi-solid. What this means, they have 0.5% agar. This agar concentration here, obviously, sorry, this need agar. This agar usually 15 gram in 1,000 liter. Then you have 0.5% of agar. This is usually 7.5 gram in 1 liter of water. Now, what's the function of that? Semi-solid agar, there's a two functions. One function we did using the lab all the time, which is testing motility. So remember, bacterial flagella decided whether bacteria can do real movement or not. So we're using a semi-solid agar. We put a needle inside and we took it out. Like a stab. What happened is, I'm going to draw this a little bit large, okay? That's too small. What happened is, we're going to do stab, come in, come out. If the bacteria do not have a very strong motility capability, what they do? They stay right in the middle. So they stay in the middle. No motility. Now, how do you know the bacteria have a strong motility? If the whole plate is moved around, that is called motility. Now, which bacteria has a strong motility? Proteus vulgaris. Because it is petrotrichous. The flagella is everywhere. Now, which bacteria do not have motility? Stay in the middle, Pseudomonas. Because Pseudomonas is monotrichous. Only one flagella on one end. So just want to let you know, they do have a semi-solid medium to test motility. It's very, very interesting. Okay. Second thing what I want, this is the category. Second thing I want to mention is the defined medium. Versus complex medium. So, this is the concept for lots of people always misunderstanding. What is defined medium? Defined medium, which means defined medium means every each individual chemicals are well defined in the medium label. Otherwise, it is complex media. Okay, now there's a question for you all the time. Okay, in a media, I have water 70%, sodium chloride 2%, beef extract 1%, peptone 2%, tryptone 5%, let's say glucose 10%. Let's say, okay. Is this a defined media or is this a complex media? I don't ask a question all the time. Can somebody tell me, if I have a label of a media which is water 70%, sodium chloride 2%, beef extract 1%, peptone 2%, tryptone 5%, glucose 10%, is this a defined media or a complex media? Can somebody tell me? Yes?
Is it complex?
Yes, why?
Because, I mean, like number 3 is like beef extract, but you don't really know it's in that.
Very good. That's a question, that's the answer I like it. I did that question all the time. Lots of people will tell me this is a defined media. It is wrong. Why? Although there is a name of these, there is a concentration of that, but we don't know what's inside of the chemicals in peptone. As I said, it's a derived protein. We don't know what's inside of beef extract. There's millions of chemicals there. So, if you see this happens, this is a complex media. Now, what are the examples of defined media? If they tells you salt, they tells you sodium monophosphates, they tells you sodium hydroxide, they tells you components of potassium phosphate. If they tells you each of these chemicals very, very well, therefore this is a defined media. The key here is all these chemicals, and this is a pure chemicals. That is the key. So give you some of the example. You can look at the slides. Everything below, you have neutral gloss, which is peptone beef extract. Although they tell you the amount, we don't know exactly what the chemicals inside. So it's a complex media. Neutral gloss we do all the time in the lab. The second one we do lots in the lab is tryptic soil gloss. Acronym TSP, the second one. You see glucose, sodium chloride, dipotassium phosphates, peptone, tryptone. We don't know which is peptone. We don't know which is the peptone. So it's a complex medium. Macaque agar, we're going to mention real quick. You have lactose. You have biosalts. You don't know what's inside. You have casein. We don't know what's inside the related chemicals. So that's a complex medium. Now, what is a defined media? You look on the top. The defined media, you see every single chemicals is well defined. Now, what we are using for this defined media? These defined media compared to complex media, most of the time is poor nutrition. We actually grow biofilm in the lab. So biofilm grow really well in the poor nutrition media. These are really the lab media. That's BG11, that's a lab media. Okay? It's relatively poor nutrition media. We can say that. Compared to the tryptic soil gloss and the macaque agar and the neutral gloss. Okay. This is a peptone. It tells you what is peptone. Protein hydrolytes prepared by partial digestion of various protein sources. Aqueous extract. Now agar is polysaccharides. We know that from seaweed created by Fanny Hesse, Bob Koch's research associate a long time ago. She's the first person who find using polysaccharides from seaweeds, using agar is a solid medium. And we have then the Richard Petri have the container, which is we call it a Petri dish. Okay, so these are stories you could go back to review. Next one. It's a function type of the media. This is relatively difficult. I'm going to move all these to the side. Then to explain these things to you. I have a couple of bacterial media here. We'll give you an example. Okay. Based on the function, bacterial media could have a different category. Number one, support media. What means support media? Give you an example. Trophic soil broth, nutrient broth, which means a normal bacteria medium will support most vegetative bacterial growth. And then what is the level they will grow? At 35 degrees Celsius, 24 hours, they will grow to 10 to the 8 to 9 cells per ml, which you can transfer. This is 8 to 9 log 10 CFU per ml. And the other place looks very, turbidity looks very density. It's a supported media. Now, why I say most vegetative cell? Which bacteria will not grow? Except fastidious bacteria. Fastidious bacteria is very picky for the condition. A good example, Campylobacter, we just mentioned, and the Haemophilus influenza will cause meningitis of child. It is the number one childhood disease. Cause meningitis, Haemophilus influenza cause meningitis. These are fastidious bacteria. Even Neisseria gonorrhea causes sexually transmitted disease. Neisseria is a fastidious bacteria. These fastidious bacteria are not going to grow in a normal bacterial broth, which means trophic soil broth, nutrient broth, TSB, MB will not grow. So that's called supported media. Support the majority of the vegetative cells at 35 degrees Celsius. After 24-hour incubation, they grow dramatically to 10 to the 8 to 9 cells per minute. Okay, the second one, enriched media. Enriched media, which means you add certain ingredients will dramatically support bacterial growth. This is also non-fastidious bacteria. A good example, I will use red color to show you, is blood agar. This is the example. A good example is blood agar. Because it's a blood agar, obviously is red. This is blood agar, very red, look like a blood. Now, what is this blood comes from? You think it's from a human being? No. Where they come from? Sheep. Okay, this is from containing 70% of sheep blood. Now, how they made it? Trophic soil broth, add agar. This is a base. And then we add 70% sheep blood. Now, why we use sheep blood? Because in 1970s, people find the sheep blood, the biochemical characteristics equals human blood. So we can use it, replace of the human blood. It will be the same thing. That's a blood agar. So blood agar is an enrichment media. Why do we have enriched media? What's the major ingredients of blood? Hemoglobin. That's a huge, ions is there. Is that right? All kinds of the chemical nutrients there. So will support the bacteria grow dramatically. We could make even a chocolate soil broth, you add blood there. It will grow dramatically. But usually 10 to the 10, 10 to the powers of 10 cells per ml. Now why we need that amount of the bacteria? Because in the medical area we need a huge amount to do the diagnosis. Sometimes we need to extract DNA, RNA, or some of the other things to do the work. Maybe the protein of the bacteria. Okay, that's why we need using a blood agar. Okay, the next one. There is another enriched media, which is called chocolate agar. This is a very funny name, chocolate agar. What it looks like? Looks like this. It's a chocolate agar. I have another funny one for you. Like a pancake. Huge. Chocolate agar. Okay, now there's a question. Do you think there's a chocolate there? No, there's no chocolate there. Chocolate agar is not a candy ball you add into the media and then become a chocolate. No. It is, the full name is chocolate-like agar. How they do that? It is blood agar heated at 70 degrees Celsius, turn brownish, a little bit of purple, turn brownish, looks like chocolate. So it should say chocolate-like agar. And the quotation mark. But every people who made it, who think you are very smart, everybody is really smart. So they skip this, and they connected it, become a chocolate agar. But it's not a candy ball, okay? What is a chocolate agar for? Cultivation of fastidious bacteria. Let's say Haemophilus influenza, Neisseria gonorrhea, they only grow on chocolate agar, not even on blood agar. Now for Campylobacter, they not only need chocolate agar, they need other ingredients. So we call it a modified chocolate agar. Lots of the agar, the transport medium is modified chocolate agar. Let's say we have a modified called Siamodi media, which is for Corynebacterial diphtheria. If you have a Corynebacterial diphtheria happens, you need to report to CDC. Then the patient, the throat culture needs to go to the transport media. That's a modified Siamodi media, is a modified chocolate agar. So chocolate agar is an enriched media, but it's very special. But there's no chocolate there. Always remember. Okay, this is an enriched media. The next category, differentiated media. What is a differentiated media? Certain ingredients there, after bacteria grow, will have a different biochemistry reaction. So I will say is that certain ingredients generate different biochemical reaction. Most likely, of course, on others, okay, most likely, it's a color change. And lots of the time, it's turned black, I can tell you. And we will mention several examples. Most of the time, turn black. But not really, not all the time, most of the time, turn black. So that's a differentiated medium. And I gave you an example. I have Enterococcus facilis. Enterococcus facilis. This bacteria, my students will mention, it's a surrogate bacteria for Salmonella. This bacteria can grow in bile S-culin agar. And this S-culin is a very traditional Chinese herb. If the bacteria grows there, the S-culin will become S-culating and turn black. The colony turns black. So there's a biochemistry reaction there, so it turns black. But we don't often see that. Another good example for the differentiated media is going back to talk about the blood agar. Why? Because the bacteria could be hydrolyzed, different bacteria on blood agar could hydrolyze the blood cell. Therefore, based on the bacteria's growth situation on the blood agar, we could categorize it into alpha hemolytic. Do I have an example here? I think I have one. Right here. Alpha hemolytic. This is incomplete hydrolysis of blood cell. So what's the color looks like? The bacteria, the color grown there looks like green. Sometimes dark green. Which bacteria is that? Streptococcus pneumoniae. This is the #1 community-acquired ammonia in the United States, called Streptococcus pneumoniae. That's called alpha hemolytic. Okay, since we have alpha hemolytic, we have second one, beta hemolytic. Beta hemolytic, which means a complete hydrolyze of blood cell, will generate a transparent zone. A good example, Streptococcus pyogenes, called in strep throat. That's the example. On the top, beta hemolytic is a transparent zone. I will generate one for you later on. Let you see. So beautiful. It's a transparent. When you hang on like this, you couldn't see the other side. Okay. Now there is another category. Nothing happens. Gamma hemolytic. These three hemolytic is very important. We will talk about this again in the exams too when we talk about the pathogens. Because in the clinical area, we want you a rapid diagnose. What we do, we're using blood agar. But I want to tell you one thing, the blood agar cannot always do. Some of the biochemistry tests, like the catalase test, you cannot use blood agar. Because catalase test is to test the oxygen generator. And on the blood agar, they already have oxygen. So if you use blood agar, the oxygen comes out, will give you a false positive. So keep in mind, it does not mean it's so magic, although it's used widely in the clinical area. Okay, the next one is we call selective media. So what is selective media? This is number 5. Selective media, which means they containing certain ingredients, will favor only one group of bacteria. That one group of bacteria could be only favor gram-positive, and the gram-negative bacteria will be died. Maybe only favor gram-negative bacteria, gram-positive bacteria will be died. And I give you a very simple example how you understand this. I have a tropic soil agar, TSA. I'm going to add 100 parts per million penicillin. Which bacteria will grow, do you think? Penicillin-resistant bacteria can grow. Is that right? The majority of the bacteria will be killed because penicillin is a broad-spectrum antibiotics. So which bacteria will grow? Only penicillin-resistant bacteria can grow. Others will be died. That's a selective medium. That's a very simple example. So why we want to mention this? Because penicillin resistance happens all the time. We will talk about antibiotics later on. We have a penicillin G, penicillin V, then become a methicillin. Then methicillin becomes a resistant called MRSA, methicillin-resistant Staphylococcus aureus. Then we become amoxicillin, ampicillin, all kinds of things will generate. We'll talk about it later on. So just give you a hint here. Okay, now what's a difficult thing for these things?